I'm recording now.
All right, sweet. All right, actually, let me share a different screen real quick. All right, can everyone see this okay?
Yeah, I can see it.
Okay, so I guess this is like how you would make a project that uses an RTOS is implemented. So right here you have your int main, and then you initialize like anything like the OS related stuff, and then you add threads and OS start. So that like this is like pretty much the standard structure. Actually, let me go back real quick. I think I forgot to mention something. But an RTOS, for anyone that isn't familiar with it, means a real-time operating system, and it's different from like. So like you have to call this or do a specific task or do some IO function at like a really specific deadline with a really specific deadline. And also an RTOS is like more, I guess, there's a lot less. It's a lot smaller than actual OS, and I guess the scheduling methods, like deciding which tasks to run, is also a lot more different. But so there are like concepts that you can apply of RTOS that you can apply to an OS, but it's not the exact same. So just to make a note of that. So okay, I'll just go ahead and start doing this demo, unless if anyone has any questions at the moment. Okay, all right. So pretty much this is like the setup of how you would make a project, a program that uses an RTOS or an OS in general. So there's this OS init task and an OS start. So init just initializes anything RTOS related. And then to create threads, you would usually call some type of add thread function. There's a lot more parameters usually, but just to simplify it, I have like just these two parameters, which is passing in the function that's going to be your task, and then the priority. So basically, like I like to think of tasks or threads as their own int main functions. So like pretty much you can run this inside, like you can just make this int main and you can just run it, and the same with the rest of them. But yeah, these tasks, you can see that they're in descending priority levels. So add has highest priority, and the idle task has the lowest priority. Yeah, you'll notice that. Oops, I forgot to change this. But you'll notice that I didn't add a thread for the idle task, and it'll make more sense once I start doing the demo. But an idle task is one like the default task that needs to be present, or else the OS will like crash. But these tasks, I guess in terms of RTOS like context, it's easier to view them in the assembly equivalent. And just to note, or just to preface my everything, some of these implementations, like you may see like bugs or something like that, or like, oh, this isn't like really the correct way it works. But the only reason why I made those shortcuts is because of time. There's like a lot of stuff that you can go over, and that's going to be more time than I would. I don't want to waste your time. But just to know if you see any errors, is just a shortcut I have to take. And this demo right here will be like not actually like how everything works, but it's like a really high level like view of how it would the concepts of how it would work. But you can see the assembly equivalent of each task right here. And I have it right here. But in case anyone wants to see like the C equivalent while I'm doing, the C equivalent while I'm doing the demo, then you can go to that link that I showed and then click the .c file. Okay, I'm going to start sharing my other screen now. And then if anyone has like any questions or if something's unclear, you can just like stop me and just ask. And also, I may not be looking at the chat window that often. I'll try to, but in case like I don't see it, just straight up just interrupt me and ask. Okay. So pretty much an RTOS. So each program or each thread has its own context, meaning like the CPU views each thread independently. So the CPU has like all these registers, the general purpose registers, and like the stack pointer, link register, and program counter. Right here, to simplify it, I don't have the whole register set. I just have part of it. But each thread has its own context, meaning each thread has its own state of the CPU. And all that information is stored in what's called TCBs, or thread control blocks, and pretty much has like the stack pointer and stuff like that. I can show you. But it's pretty much just a struct that has like important information, like what priority that thread is or something like that. Yeah, so a TCB holds important information about a thread, a single thread. So right here, so after you call like, after you run the int main function in C and like add all the threads, each of these tasks or threads will have its own TCB. So, and are you able to see this? Is everyone able to see this right now? Like at least the text.
I can see it.
Okay, sweet. Let me know if something's unclear. I can try zooming in, whenever possible. Okay, so whenever you call those add thread functions or create thread functions, it will create a TCB for that thread. And in each TCB, it'll like hold like all the important information about that thread. But so you'll see how like, actually I'll copy this in. You'll see how you added, I added a thread called add task, and has a priority 0. So pretty much there's just going to be a list of active TCBs, and the list of active TCBs is just going to point to a certain TCB. So add task is priority 0, multiply task is priority 1, and then subtask is priority 3. And then idle task is like internal to the like default. Sometimes you may need to add it manually, but most of the time it should be able to. It should create its own idle task. The RTOS would, and it's always the lowest priority in the whole system.
Just a quick question: can two tasks have the same priority?
Yeah. So right now I'll be showing a priority scheduler, just like a simple priority scheduler. But you can have there's also like different types of schedules, like round robin, which is pretty much like there's no priority. There's a time slice for each task to run, and it'll just loop across each task. But you can have a hybrid of a priority schedule that implements round robin per priority. So you can most RTOSes will be able to handle that. So you can have like 2 threads of the same priority, and it's just going to round robin in that priority. Okay, so now after you add all the threads, once you get to OS start, there's going to be a pointer to like which TCB is currently running right now, and I indicate this by this run pointer, or this run triangle. So once OS start is called, this run pointer is going to call a scheduler. And right now we're doing a priority scheduler. So it's going to find the highest priority, and it will start running this task right here. So the highest active priority right now is add task. And the RTOS internally will get the context of that task. Pretty much the CPU, like all the registers on the CPU and the stack it's using will all be replaced with that task's registers and stack. So actually, let me change this real quick. So these are the addresses. So this will be PC will be pointing to that, and the PC will be that multiplied task. Okay. So right now the CPU will have these registers and the stack. All right. So whenever you first so for the first function is the semaphore. A semaphore is pretty much like just a flag. And if that flag is not set, then you just wait until it is set. And these semaphores are usually blocking statements, meaning that once, if you see that the flag is not available or the semaphore is not available, then it will block itself, meaning that the TCB, that thread will no longer be an active thread. So after executing OS semaphore pen, so right now, it'll see that the flag is not set currently. So it'll have to wait. So the RTOS will block that task. So it'll be like inside of another list that's blocked. And then the RTOS will run, and the RTOS scheduler will run. It will see that the next highest priority task is a multiplied task. So it will get the context of this now. So the CPU will save everything for this task, and then it will now load in everything from this.
I have a quick question. Is the blocking like the add task, for example, would that happen inside of the like OS semaphore pen routine, or is that like when you return, there would be some assembly to check if you were blocked or not?
Can you say that question again?
Yeah. So is whenever you call semaphore pen, inside of that subroutine, is that where you would decide if your task is blocked, and if it is, you put it in blocked tasks?
Yeah. It's an RTOS function, so inside of it, I'll just call RTOS related functionality to make a block after deciding or after knowing if it's available or not.
Okay.
Yeah.
What would be an example of why a task is blocked?
So the main thing is whenever a resource is not available. So let me show quick. Okay, so actually, I guess I can just show this. Can you see this okay?
Yeah, I can see it.
Yep. Okay, so I guess I have two examples. One is synchronization, and one is making an operation atomic. So for the synchronization part, say you want to have print 1 and 2 together, or in this certain pattern. So you can have it so that so the OS semaphore pend function, it will see that this function is not available, so it should block itself. So then the next available task, which is thread 2, will run. All right, let me get back to this because I can go through how the blocking works first, and then I can show you an example. Is that okay?
Yeah, sounds good.
Okay. Okay, so this task has been blocked, and then the context for the next active highest priority task will be loaded into the CPU. So now all these registers are set, and also the PC has changed. So now the PC is now pointing to the last line of code that it left off at in the other task. So PC is now updated, and then now this semaphore post, semaphore pen just means waiting for a flag. Semaphore post means setting a flag. So this isn't a blocking function, but after this inside this function, this semaphore post function, it will unblock any task that is waiting for that flag, which is actually, let me copy this in. So this task, right now we're on this task right now. This post function will set the count semaphore flag. So internally inside this function, it will unblock any task that's waiting for that thread or for that flag. Since it unblocks any tasks that are waiting for that flag, the RTOS internally will get the blocked task and then place it back onto the active TCB list. And then the scheduler will run, and then it'll see that the next task, the highest priority task is add task again. So now this, So the contents of the multiply task will now be saved, and then the add task will not be loaded again since the new thread, the highest priority is add task now. Okay, so now PC is now back here. So now this now it came out of this function now. So it's now executing the next line of code, which is just sum plus plus. So that this is the assembly equivalent. It's not like one-to-one, but it's like similar. Still grab the address of sum, and then get the value of sum, and then increment it by 1, and then store it back into sum. So now the sum variable is now 1, and then it will branch back to add task. So now it will go back here to the blocking, or to this blocking function, and now it has to wait for the flag, since after you call semaphore pend, you grab that flag, and unless if you set that flag back again, it will always be grabbed. So like the flag, it will not be available now. I can show you an example of like what situation would you need to like grab a flag and then set the flag again in like one operation, or not one operation, but like in one task. But for now, in this context, semaphore pend only grabs flags and semaphore post only takes flags. So now it's back here, and now it's waiting for this semaphore. The thing is, now it's not available anymore. So the RTOS will block this task. So now this task will go back to a block function. And then the RTOS, actually, real quick, these variables changed a little. Or not. And then this is like the sum. And now it's back to that address. So the RTOS will now find the next highest priority task, will save the previous task context, and then load in the new task context. And now PC is back to here. And then now, since it already called this function, it's going to go to the next one. So this assembly function right here is equivalent of just multiplying by 2 and then storing it. So I'm going to increment until I get to this OS sleep task right here. And OS sleep just means that it's going to go to sleep, meaning the task will be blocked. It's just, pretty much just that. So by the time it reaches here, it's going to go to sleep. But then let me change this real quick. So the value of multiply has been multiplied by 2. And then R1, actually, this is now 1, actually, sorry. Since I had to move it R0, or hex 1 to R0 after storing it. So now it's here, and then PC is also updated. And now it's going to go to sleep. So now it's going to just block itself for a certain amount of time. So now this is going to block itself, and then the RTOS schedule will find the next highest priority task, which is sub task. So it will save this context, and then it'll load in the new task context. And then it'll see that the PC has changed, so now it's going to go to hex 3000. And then it's going to just execute these lines of code until it gets to the next blocking function. And pretty much this assembly code is equivalent to just subtracting 1. And then it's going to go to sleep for 10 milliseconds when it gets to the OS sleep function. After this will be 10. This will be sub. And then this is going to block itself. And the blocking all happens inside the function itself, and inside the OS specific functions. So now after blocked itself, the OS will try to find the next highest priority task. So the next highest priority task is the idle task. But say we didn't have an idle task, say this wasn't there. So the next available TCB is a null. So whenever it's going to try to load the context of a null pointer. So that's why you need to always have an idle task or like some type of task at the lowest priority task where it will always run if there's nothing else to run. So since this the OS found the next highest priority task, which is idle, and then it's going to save the current context and then load in the next context. And then PC will point wherever to idle is. And then once, so and then it will save this context, this PC's context.
Sorry, you cut out. What just happened?
Oh,
I mean, I think I cut out, but yeah.
Do you know when you cut out? Should I explain?
Yeah, right. Oh. We were in the idle task, and you were about to start talking about how we get out of it.
Okay, all right. So pretty much. So right now, it's so after the idle task runs file. So one of these functions will be called once it becomes unblocked. We have multiply task right here to wake up after 1 millisecond. So once that timer ends, it's going to the RTOS will automatically unblock that task. So once it unblocks that task, it's going to put the multiply task back into the priority level that it was originally at, and then the RTOS schedule will now find the next highest priority task, and then it'll see a multiply task, and then it will save the context of idle task and then load in multiply task. Okay, and then the PC has been updated to here now from the idle task, wherever it was in the idle task to here now. And then since it just execute OS state, it's going to go back and loop and then call summer for post. And then summer for post will unblock add task. And then the RTOS schedule will now check if there's a new highest priority task, which there is. And then we'll go execute the add task now. And now the RTOS will save this context and then load the context of add task now. And then the PC is now new. It's going to go through this, and then it's going to go back and loop. So sum is now 2 now, and it's going to block. The OS sum for pen will block now. So this will be blocked, and then the RTOS schedule will see that this is the next highest priority task. Oh, wait, this is the wrong level. This is the next highest priority task. So it will save this context, and then get the context of multiply task. And then PC now updated to here, but now since it woke up, actually no, sorry, I forgot to update this. But after it woke up and after add task was called, it's now going to go execute the next line, which is just multiplying by 2 and then calling OS sleep again. Now the PC is 18, and this is now 4. And then OS sleep will block this task. And then the RTOS schedule will now see the idle task is now running, and then it'll point to whatever it last left off in the idle task. I'm also changing this context as well, sorry. So that process is pretty much going to keep happening until subtask wakes up, but yeah, pretty much that's how this function, how the RTOS will handle executing this these tasks. Does anyone have anything that Or did I say anything that was like confusing or not clear?
Just a quick question. How often is it checking for the active TCBs? Can it do it mid-instruction, or is it like after every instruction?
So when checking, like, so usually you'll have like a scheduler function that like checks and like just sees like what's the next TCB that should run, and returns like a pointer to the TCB. But you can either have it where you have a SysTick timer. So a SysTick timer is like, even though like we use it in 319K as just a timer, SysTick's original purpose is to keep track of time for an RTOS or an OS. But so you would use like, you can use a SysTick timer to like interrupt every interval, like turn certain time slice or a certain time interval, and then you can call the OS scheduler and see if there's a new active task. Usually with priority schedulers, it's mainly whenever you unblock or block anything, then the OS schedule will run. Okay, did that answer your question? Yeah. Okay, sweet. Anything else?
Yeah, so basically the idle task is there to just stall time until another task becomes available again?
Right.
Okay.
Yeah. If anyone has any more questions about like this, then I can go over it more afterwards. But so I have, but I'll continue. So I made these slides. They're not really like, there's a lot of information, so it doesn't have everything. I've pretty much gone over like an RTOS, like what an RTOS is, like what tasks look like or a thread looks like. So multi-threading, I showed how multi-threading works, but technically there's no concurrency per se. It's like pseudo concurrency. And concurrency just means that like operations are running like at this exact same time. The TM4C and the STM32 that we use for our systems, they only have one core, meaning that there's only one like set of registers, one CPU, and one CPU means only one program counter. So it can only execute one instruction at a time. So the RTOS pretty much creates an illusion of concurrency by making the PC jump everywhere between tasks to make it look like that everything is running at the same time. When a context switch, when I was explaining like how these registers and the stack gets loaded every time a task switches, it's you usually hear it in terms of like a context switch, meaning like the context of that thread or program is now being changed. And a context is just like general purpose register, stack pointer, PC, and stuff like that in the program. TCB just holds like the context. It's like the actual data structure that you would use in your OS code to store everything. And you'll see right here, there's nowhere really about like the general purpose registers that I've been mentioning and like PC and LR. That's because everything gets pushed onto the stack. Just in case if anyone had a note, I can go over more later whenever we're going to source code after this.
So do you just allocate specific memory for each task and they use that as their stack?
Yeah. So the like one main difference between an RTOS and OS is like dynamic allocation. So you can have a heap with an RTOS, but I guess in terms of a system, it's not really, I guess, ideal since it's not like dynamic memory allocation isn't really I guess what's for it? I guess it's not predictable. So usually, whenever like you're making a TCB, like whenever you're adding a thread, you'll statically allocate your own stack, and pretty much that stack it will be saved on the stack pointer. Did that answer your question, Rishi?
Yeah.
Okay, sweet. Yeah, so this is like a very basic like TCB that I took from my OS that when I took the 445 line class. The next and previous, it's mainly for like hybrid and round robin schedulers. I can go over that in a bit. So the CPU state is pretty much the state of all the registers. So the ARM has a standard where like whenever you call a function, you can assume that R0 to R3 and R12, they can be freely modified and they contain like the input parameters for that function. And R13 to R15, the very end registers, they're like dedicated for a specific purpose, like at the PC or the LR and so forth. The thing is, with each thread has its own context. So that means that all the registers, even R4 through R11 and R0 to R3 and R12, like even the ones that you can freely modify when there's a rule that you can freely modify it inside of a function, those still needs to be saved because that rule to freely modify it is only in terms of its own thread and not in terms of the whole system in general. Did that make sense? I don't know if that made sense or not. But basically, every single register needs to be saved. And the way most RTOS implementations do it is they don't save it to a certain variable, they save it onto the stack. And there's a reason why it's saved onto the stack, and it's because of how interrupts work. So in RTOS, like the kernel itself, like the actual like bare metal, like very low, like when RTOS is actually like how it actually runs, it's all handled inside of an interrupt handler. And I don't know if just as a reminder, whenever an interrupt occurs, R0 to R3, R12, and then these registers, they're all pushed onto the stack before any code is executed inside the handler. But the thing is, if we only push those registers, if the interrupt only pushes those registers, it is the user's, or I guess the handler's job to push the rest of the registers. So this is like a pseudocode of like an RTOS, pretty much the whole RTOS. So there's this something called PendSV, and PendSV is like similar to Sysdig, where these two interrupt handlers are meant for an RTOS. ARM created them and designed them so that an RTOS or an OS would use those. And a PendSV handler is pretty much, you can think of it as like, it's a hardware interrupt that's triggered by software. So to trigger this, so usually GPIO handler or GPIO interrupts, like if a GPIO pin like becomes high or becomes low, then the interrupt would be triggered, and then you would call the GPIO handler, right? But in terms of PendSV, you have to set a bit in the certain NVIC register, and whenever you set that bit, then the PendSV interrupt handler gets called. And this is the pseudocode. So like I mentioned earlier, R0 to R3 and the rest of those registers that are already, they're pushed onto the stack before the interrupt handler runs. And then now it's our job to push the rest of the registers and then save the stack pointer to the TCB. So the stack pointer will always be changing. So the state of the stack pointer, where like after pushing everything, that needs to be saved to the TCB, to that thread's TCB. And then you'll choose the next thread and then retrieve the new stack pointer and then restore the new thread's R4 to R11 registers. And then once you get out the interrupt, since the stack pointer is now new, it will pop off R0 to R3 and the rest of the registers when it exits the interrupt. So this blue part is meant for the blue assembly code is for like the currently running TCB or currently running thread. The black lines of code is actually like switching between like the actual act of switching from one thread to another. And then the red code is to load, restore the new thread's registers.
Okay, so the R4 through R11 that you're popping, that's not the same as the R4 through R11 that you pushed, right? They're two different thread registers.
Right. Yeah.
It's popping from the new stack pointer, right?
Right. And then scheduling, there's a lot of different scheduling methods. You may hear like cooperative scheduling and preemptive scheduling. But cooperative means like you have to call like a yield function in your thread itself in order for the RTOS to make a context switch. And then preemptive is like how priority schedulers work or round robin schedulers work. There's an interrupt that will switch threads. Underneath preemptive scheduling, there's like the priority scheduler, which is what we went through, and there's a round robin scheduler. Pretty much each TCB, it's pretty much like a circular linked list of TCBs, and the scheduler will just like get the next TCBs because the next TCB whenever it like is trying to decide the next thread to run. And then there's a hybrid. This is what's most commonly used now. It's a priority / round robin hybrid, and pretty much means that each level of priority there's a round robin, or like it's using round robin. So like here, to say you have like add task and multiply task and subtask right here. So basically, to have round robin, you need to have like time slices or like some type of timing. So in this case, it will be a static interrupt, and once the time slice ends, it will go to the next TCB, and then pretty much it will point back. So it's pretty much going to be round robin until, and it's going to keep round robining until both of these tasks are blocked, and then it'll go to the next highest priority, and then it'll round robin in there again. And then there's fixed scheduling, pretty much meaning like at this time you run this thread, at this time you run this thread, but this is like, so these happen during runtime. This is pretty much before runtime, or pretty much compile time, I guess. But you for fixed scheduling, you decide, you plan out when to execute each thread, and then you code that. I guess there are some use cases. I honestly haven't seen one that's useful doing this. I bet there are though, but if anyone finds that, then let me know. But preemptive scheduling is like pretty much like what Micrium uses or FreeRTOS. Now, critical sections. Honestly, I don't really remember much from 319K if we've gone over this, but I know in 445L is like one of those like main topics that are tested over. And critical sections just means that
Valvano touches on it a little bit when he teaches 319K, but I'm not sure if it's ever stressed.
Okay, all right.
I don't recall.
They just say before you do this, you should disable interrupts, and afterwards you should enable them, but they don't really go into why.
Okay. All right, sweet, thanks. But a critical section pretty much means that multiple threads are accessing a variable, and there is a possibility that there is a conflict or something can go wrong. So it's usually that you'll hear like read-write access, like read after write, write after read, and so forth. We can go over that like later if anyone is interested. But it's pretty much basically if you're editing a variable, if you're accessing a variable and like setting it and reading it, just make sure that no one else reads it. And if you do, then you need to do some special stuff with semaphores. Here's an example of what a critical section could look like. So you see here, this one line of code can be translated into these lines of assembly code. So an interrupt or a context switch can happen at any line of code or at any line of assembly instruction. So right here, you'll see that variable is being ORed with hex 1, and this thread's ORing it with hex 2. So say that the variable is 0 at the moment, and thread 1 runs. So right here, it'll like get the address, get the value of a variable into R0, and then it'll OR it and then store it. But say you get the value of a variable, which is 0 currently, into R0, and say between LDR and the OR operation, there's an interrupt, there's a context switch, making it so that thread 2 now runs. So R0 here holds 0 currently for the variable, and say now this is running. So R0 will get the value of variable, which is 0, and then OR with hex 2, and then store it into the variable. So basically, now after running this line of code, the variable will hold the value of 2. But say a context switch occurs again sometime later, and then gets back to this line of code. So now R0 is 0 right now, but technically variable is 2. So so now it's going to execute this OR function, which is ORing it with hex 1. So R0 will now be hex 1, and then store hex 1 into variable. So now technically a variable should now be hex 3, but because of this critical section, it is now hex 1. Does anyone have any questions? Or anything I should clear up, or anything that I said was confusing? Okay. All right. So critical sections, basically, if you have multiple threads accessing the same variable, then you have to be careful. And to fix critical sections, you can use semaphores, and pretty much it creates atomicity, and or they can just be used for synchronization. So to make it atomic means that once you start an operation, then it will always run, or it will complete without anything in between, or I guess without without any changes to what you're working on, or any changes to the variable you're working on. Right here, you can see here's one example. So you can add semaphores, and you can have it so that if the flag is currently, pretty much the semaphores will check if the flag is currently set, or in other words, if it's available, then grab that flag and then edit it, and then release the flag. So basically, how this will work is, say we start executing the OSM for append function. So the flag is available, or say the flag is available. So now it will take that flag. So now no one else, all the threads will know that, or will know that someone is working on this, or someone took the flag, and someone is working on something related to that variable that the flag is associated with. So I should wait. So right here, this takes the flag, edits it, and then releases the flag. So, but there's still a possibility that an interrupt will occur in between, right here in one of these assembly lines. But because of these semaphores, you'll see that when you get, say, it interrupts in between executing this line of code, once it gets to the other thread, it will, this thread will first check the semaphore if it's available. If not, then it'll just block until this is available, and once the flag is released. So this creates atomicity, meaning that the variable functions will be executed completely and accessed and read and written completely without any fear of other threads editing it in between. And then you can use it for, also quick note, you might hear the term mutex instead, or mutual exclusion, and I have it in the next slide, but it's semaphores. You can, they can be used in a way to be mutexes, just as a note. And then you can also use it for synchronization. So in this example, I have it so that it's going to be printing 1, 2, 1, 2, 1, 2, 1, 2, and so on. So right here, OSM for append, it was going to grab this flag. If it's not available yet, then it'll just wait, and then it'll call the next. It'll call the other thread. So this releases that flag. So now, once this flag is released, then it can go move on to the next line of code, which is signaling or releasing or setting the flag, this other sync2 flag, and then execute and it'll go back to waiting. And then this one, after post, it'll execute pend, see if this is available yet. If not, then wait. If it is, then go ahead and execute. I don't know if that explanation was good or not, but does anyone have questions? I can try to reward it if it was confusing. Okay. Then mutex is just an application of semaphores. You can the pen and wait and pen and post functions. You can pretty much do the exact same thing. Most RTOSes will have something separate for mutexes. So you like here like mutex lock or mutex unlock, and pretty much it does the exact same purpose. Just make sure that everything is atomic. Blocking functions, I guess in the demo, hopefully it made sense. If not, then we can go over afterwards even further. But it's just this whenever the schedule runs, it will not see a blocked function as an active thread. And then deadlocks. So with semaphores, you have to start being careful with creating deadlocks, which is pretty much the program freezing. And if the program freezes, then pretty much, I guess, yeah, just basically it's bad for a program to freeze. So in this variation, you'll see how this is slightly different from this code. So you see how it's pend post and then post pend. And this one, it's pend post and pend post. So basically, so right here, say neither of these two flags are set yet. So they're not available. So whenever thread one runs, it will call semaphore pend, and then it'll wait for this flag. So this will block itself. And now this thread will run. But whenever this thread runs, then it's going to wait. It's going to call this function, and it's going to wait for the second semaphore. The thing is that one's not available either. So this will block. But the thing is, both of them are now blocked, and that creates a deadlock where nothing is actually running now, since there are dependencies between them that are preventing other stuff, preventing the threads to run. And these 4 parameters of like how a deadlock happens, you'll hear in both like the RTOS class and the OS class, but if these standards are met, then there's a deadlock. And I have some backup slides just in case anyone wants to go further. So like RTOS versus OS, and then priority inversion. Because like once you start blocking stuff, then and doing priority level scheduling, there's going to be some weird priority level issues that will occur. But since we're getting close to 3 now, then I can go over this at a later time or afterwards if anyone is like super interested in how to deal with this. But yeah. Does anyone have like any questions? I know this was like a lot of information, sorry.
So the Micrium RTOS, when I was trying to get it to work with a Linux port, it said that you needed to have some sort of OS function called at the end of or during each of your threads. So is that still what the preemptive scheduling?
I did see that as well. I guess I might need to check back in on you with that. But there's technically you're still triggering an interrupt whenever you do like. Actually, hold up. So there is still technically preemptive scheduling, even though it like says you need to call on these functions with like the timer or something like that. But I need to look into Micrium documentation again. I saw that before as well, and I thought it was weird. But yeah, I'll let you know.
Okay, thanks.
And for the if anyone here is not taken like 306 or 319K, I'm guessing a lot of that probably went over your head. Next week, I'm probably going to have a lecture over like basics of how a CPU works, cover some of the material from 306, and then after that, maybe the same week or maybe the next week, Sijin can go over this again, and it make more sense.
Yeah. I don't know if anyone is still interested in going over source code, to be honest. That was like a lot and like a long tutorial. But if anyone is, just let me know. Oh, actually, Clark, did you want to go over like how the linked listing works, or was I able to explain it? Okay.
Yeah, sure. I guess we can go over it.
Okay. Well,
I guess that's kind of getting into the source code. I understand algorithmically how this works. I guess I will stop recording for now, and I'll put this on the Google Drive.
Okay.